Okay, 6.3, mass and density. I was having a little trouble with this camera on the program, and looks like it's working now. Okay, on 6.3, I spent the first day being a little bit over dramatic about what mass is and what density is. And there's a lot of confusion amongst students about what mass is, and about most people. Mass is not the weight of an object. Mass is just the material that makes up an object. Let's say this is my object, and inside it has protons, neutrons, electrons, atoms, a bunch of atoms in here that make it up. Okay, material that makes it up. That mass can be packed tightly together. If you think maybe of a balloon or a lead ball, the atoms are packed closely together and they're big atoms, versus a balloon, the air molecules take up a lot of space because they're moving around and they're hitting each other, and so the air in the balloon doesn't have very much mass to it. So they could be the same size, but the densities would be different. The amount of mass in lead per unit volume, and your volume could be measured in cubic centimeters or cubic meters or cubic inches or whatever. But the amount of material in there is called the mass, and the amount of material per square unit, or cubic unit, per cubic unit is the density. Now, not to be confused with weight. And weight is the attraction between two different masses. So these two masses, mass for some reason, and we haven't figured out why, what the principle is, but two masses attract and they pull towards each other, and if you put a scale in between them, like a bathroom scale, it'll tell you how much force there is pulling them together. That force is called the weight. We're kind of used to standing on the earth on top of a scale on the earth and watching the scale read some kind of numbers for the weight. All it's measuring is how much our mass is attracted to the Earth's mass. How much are they pulled towards each other? That's weight. Weight in the English system is measured in pounds. Weight in the metric system is measured in newtons. Mass in the metric system is mass, the amount of material making up the stuff, in the metric system is measured in grams or thousands of grams, kilograms, or something like that. In the English system, we who live in America and use the English system and talk about pounds, we don't talk about our mass very much. Our mass could be measured in slugs, and many people, when they hear the word slug, they're thinking about that creature that crawls on the ground and is slimy. But that's not the kind of slug we're talking about. We're talking about the slug that's the old folks with their musket rifles would put a lead ball in there, the rifle, and their black powder and shoot it out, and it comes out as a slug. They used lead weights called slugs to calculate mass. Now that seems like, well, if it's a lead weight, then we're measuring weight, but we would count them, and how many slugs have the equal attraction to the earth as so many, as some other weights. So, just to clarify, our weight, if we move up into a spacecraft far from Earth, our weight gets less because our masses are further apart. The distance between them controls how much our weight is. But as we move up, the molecules that make us up are the same amount, and so our mass stays the same. So mass isn't affected by how high we are or how far we are from some other object. The amount of material that makes up something stays the same. The weight changes depending on how close two things are together or not. Okay? So, there is a little bit of not real good clarity in this section on the distinction between mass and weight. So, again, our mass is measured in grams or kilograms. Weight in newtons. By the way, a newton is how much 1 kilogram it is attracted to the earth. There's a pull on a kilogram. A kilogram, by the way, is 1 decimeter by 1 decimeter cube of water. That's what 1 kilogram of is kind of a standard for it. 10 centimeters by 10 centimeters by 10 centimeters of water has a mass of 1 kilogram, and if you were to pick it up, it'll weigh 9.8 newtons, named after Sir Isaac Newton. 9.8 comes from the acceleration due to gravity in the metric system. So 9.8 times 1 is that's what 1 newton is. 9.8 newtons is what this is, and 1 newton is just anyway, forget that. But 1 liter, that's what this is, 1 liter, 10 centimeters, 10 centimeters, 10. About a quart of water is 10 newtons-ish. Okay? So you've picked up a quart of water, that's what about 10 newtons weighs. That's the weight of 10 newtons. And in the English system, in pounds, 1 kilogram weighs about 2.2 pounds. Now, some of you have traveled to countries where they measure things in kilograms, and sometimes you can buy your bathroom scale that will say your weight in pounds, lbs, and in kgs, kilograms, and that's a misnomer. Pounds is a measure of force, how much force you're being attracted to the earth. Kilograms on the scale is assuming that this scale is at sea level, and making this conversion of 2.2 pounds is what a kilogram of mass weighs, and so it will take the force and divide it by the force in pounds divided by 2.2, and it'll give you an estimate for your mass, but that's only if you're standing at sea level. If you go higher than that or closer to the center of the earth, that will change. But your mass so it gives you an incorrect reading for mass, even though it's giving you a mass unit. Okay, enough on mass. But it's kind of essential that you understand it to get an idea of what they're talking about on here. So Dirk said, consider a thin bar length B, so from one end to the other is B, and where X left end is at 0, so 0 to B, and assume that it has the same cross-sectional area. So if this was a circle, the area of the slice of this, if we took a slice in here, is 1 centimeter squared. So the radius is less than 1 because it's pi r squared, and pi is 3 already, so the radius has to be smaller than 1 to make this have a 1 centimeter if it's a cylindrical shaped rod, okay? So let P rho of x, it looks like P of x, but that's rho of x, represent the mass density function of the bar, which they're trying to say is this bar could be the same number of molecules packed in it per slice, per change in x, per inch, per whatever, per centimeter, all the way down, and then it would have uniform density. Or it could be the molecules packed tighter here and not so tight here. Maybe this rod is made out of oak going to balsa wood, which would be heavy, dense to light, or it might be balsa wood to oak, or it might be iron to aluminum, or aluminum to iron. Aluminum, the molecules are not as heavy and not packed so tight, and so that's why aluminum is lighter than iron. It could be made out of ice on one end and oil on the other end, all frozen, so the densities change. So it's how tightly packed the molecules are, the atoms are in here. Okay? So rho of x is measuring that. It might be getting denser here and less dense here, or vice versa, or it might be uniform all the way. So now let's see what they say about that. So they say that if you have a slice of that bar, I made a slice here, they made it someplace else, they're saying the length of it could be delta x. And if the cross-sectional area is 1 centimeter squared and the delta x is in centimeters, if you take the area of the base, the cross-sectional area, times the height of that, which would be delta x in centimeters, you get an expression for the volume of that little slice. And if it's over at x, the density there would be rho of x. And so the mass in that section would be the density, which is mass per volume, times the volume, and the centimeters squared and the centimeters would cancel the volume, and we would get the mass of that section. If we take the density times the cross-sectional area times the length of the bar we're taking. If we take those times the density, we get the mass in that piece. So that's what they're doing here. The density, which is in grams per centimeter cubed, times 1 centimeter squared for the cross-sectional area, times delta x, which is in centimeters. So you get centimeters cubed. So you get centimeters cubed times centimeters cubed. They'll cancel, and we will get the density, the number of the mass of that little section there. And since this is 1, you end up with rho times x. Now, if you want to find the mass of the whole rod, you would take the density times each little section, add them all up, which means we're doing calculus, integral. We would find the integral from 0 to b of the density of each of the slices dx that are 1 centimeter around, or 1 centimeter in cross-sectional area, so that would be a volume, 1 times this, times the density, which gives you a mass, add them all up from 0 to B, and that would be the mass of the bar. Okay, so moving on. Basically, they're saying that. So the mass will be, if the density is a function of the where you are on X, you take that times the cross-sectional area times the thickness of it, and we get the mass. So now we're going to do a few problems doing that. So now they're saying the density is in grams per centimeter. And they're saying it's got a constant cross-sectional area of 1 centimeter squared. That's how they can say that it's grams per centimeter. It's really the density, which is this function, 2e to the negative 0.2x, would be, if its density is grams per centimeter cubed, but since it's always 1 centimeter squared cross-sectional area, that cancels out 2 of those and leaves it grams per centimeter. So this isn't really density, it's the density compensated for being the same cross-sectional area all the way down the length. I would have preferred that they would have said the density is this, and that we have to put in that into the formula to find out the total mass of the rod would have been the integral from, see, the left end is at 0 and the right end it's 10 long, so we're going to go from 0 to 10 of the density, which they said is this 2e to the negative 0.2x, density times the cross-sectional area, 1 centimeter squared. We don't need to keep the units because we know that's going to cancel 2 of the centimeters in the density, times the length that we're going to take, which is just a little chunk of it, dx, which will be measured in centimeters, and that'll cancel the other centimeters and leave only the grams of the density, and so we'll get the mass in grams if you integrate that. I'm going to leave it up to you to type that into your calculator and get the answer to A. Now in B, they don't keep it a constant radius all the way down, and so that's why I don't like that they just called that 1 and made the density function different. So B, they're saying, what if there's a cone that's laying horizontally around the x-axis, the base is around, and it goes out from there. The radius is 4 meters, and just for an idea of how high that is, most houses, the rooms are 8 feet tall. The average house will have an 8-foot ceiling. 4 meters, 3 meters goes higher than that, so 4 meters would be more than 1 story high. It's more like there's how high a room would be in there. So we got this pretty tall radius going out here, 5 meters, which is 5 really large steps. So just kind of get yourself a picture of what's going on here. Okay? Now, the amount of atoms, the mass of this cone, clearly, even if it's made out of consistently the same material, there's going to be more mass in a slice down here. If I take a little slice, dx here, there's going to be more mass in it because it's bigger around than there would be in a slice out here. So this mass varies as you move out only because there's more amount of it. It's bigger around. And they, in fact, they say that let's see here. It says find the volume of the cone. Okay, let's do the find the volume of the cone. That's a pretty easy. We got a slice, and it's going to if a slice that's in this way, it's a disk. The disk method is pi r squared dx. R is from here to there. So that's the y direction. So it would be pi integral of y squared dx, going from 0 to 5, because that's where x goes from. But again, this is an x, so we're going to have to figure that one out. Well, if it goes through 4 up here, and it's a straight line because it's a cone, we get y has a y-intercept. The equation has a y-intercept of 4. And then it has a slope of down 4 over 5. So minus 4/5 x. And so this would become pi integral from 0 to 5 of 4 minus 4/5 x, that's the y, the radius, squared dx. And you could work that out using calculus. You could have also said it's 1/3 pi radius squared times the height. And this should give you the same answer. Okay, so there's the volume. Let's see. 16 times 5 is 80 thirds pi, I think. 20 times 4 is 80 thirds pi. Yes. That's the volume. Cubic meters. Okay? Let me turn that off. Okay. Now suppose it has a uniform density in this cone. So now, no matter where you pick out a cubic meter, so if this is 4, a cubic meter would be 1 like that. It's about 3 feet by 3 feet by 3 feet cube. If you pick a cube here or a cube here or a cube here or anywhere, it'll have a mass of 800 kilograms. Okay? So every cubic meter you could pick out of there will always have the same. So it's got a constant, uniform density of 800 kilograms. How much would that cubic meter weigh? Well, you would take that times 2.2 pounds, and you would get a rough idea of how much that cubic meter weighs. That's 1,600, 1,700 pounds, which is almost a ton. So this is a pretty heavy object, whatever it is. Okay, what is the mass of the solid? Now, how does this work differently? Well, we're going to do pretty much the same thing. We're going to take a slice of it, which is pi r squared dx, and that would be a volume of a slice. We're going to take the volume of the slice times the density, because the volume times density, which is mass per volume, the volumes cancel and we get the mass in there. And we're going to add all those up from 0 to 5, which would give us the total mass. Now, the reason they had us do this volume this way instead of this way is because now we can just take 800 times this integral and we'd have that. Or we could take this times 800 and we would get the total mass. But we're doing it with calculus so that we know how to do it with some other shapes that are not so obvious. But that's the idea. Now they say, what if it wasn't same amount of mass in every cubic meter as you move down the cone? What if it follows this? Well, then instead of putting the 800 in here, we would put how it changes as x increases. And if you put some numbers in here, like if x was 0, then it would be 200 divided by 1 added there. So this would be about 600 kilograms per meter cubed when we're down at this end. When we're out here, let's say let's put in 2 for x. If we move out 2 meters down this thing, what's the density here? How many kilograms of mass is there in a meter cubed? So that would be 1 plus 4, which is 5, into 200 is 40. So it'd be 440 kilograms per cubic meter. And so as you can see, as we go further down, it's going to get lighter and lighter. It's starting out at 600 and it decreases clear to let's see, whatever, 25, 26 into 200, which is 10, less than 10. So it's going to go down to almost 406 or 7 or 8 or something like that. So the mass is going to decrease. It's not going to decrease in a nice linear way. It's going to decrease by that. But it doesn't matter. We can still find out the total mass. We can't multiply it by just the volume now because it's changing. And so we need the calculus, put that into here, and we would have the total mass would be integral from 0 to 5. The pi can come out. The 800 changes to 400 plus 200 over 1 plus x squared. The density times the volume of a slice, which is going to be 4 minus 4/5 x squared dx. That's the volume of a slice times the density will give you the mass of that slice. Add up the masses all the way down. The pi makes this be the right volume. So there would be the formula for finding the total mass of this cone with the varying density. Okay, next page. So then we talked about weighted averages. And I've talked about weighted averages before with you. Let's take the grade thing, or at least for some of you. Let's say you were taking these classes, chemistry, calculus, history, and psychology, and you got a B+. That is 3.3 is supposedly a B+ from whatever school this is, and it's 5 credits, so you say, I've got 5 units of 3.3, so we got 3.3 5 times. Then a 4-credit calculus class, and you got an A-, which is a 3.7. So you take 3.7 times 4 3.7s. And since you don't have as many credits in history, it's a 3-credit class, you only get this B-, you get 2.7 times 3. And for the psychology, same thing. You must like calculus, right? Anyway, so to find your GPA, you have to take 5 of the 3.3, 4 of the 3.7, 3 of the 2.7, 3 of the 2.7, divided by how many grade credits you're taking, 5 plus 4 plus 3 plus 3, to get a GPA of 3.16. And you guys got to work on your history and psychology, get that grade point up. It's a pretty good grade point. Anyway, it's the same thing as if you were to drive 30 miles at 30 miles per hour and then drive the next 30 miles at 60 miles per hour. Some people will say, oh, my average is 45, halfway between. But if I explain to you that if you travel at 30 miles per hour it's going to take you 1 hour to travel that 30 miles. And if you travel at 60 miles an hour, it's only going to take you a half hour to do 30 miles. So you spend twice as long going 30 as you do 60. And so to get this to work right, you would have to take 30 times 2 plus 60 times 1 over 3 half hours to get the correct average. And it turns out to be 40 miles per hour. Okay? Same idea. You have to weight your averaging here. Okay, what's that have to do with what we're doing? Okay, now I want to go to something else here, and I showed this physically in class, a rod here that's got measurements on it, and I hung weights on it. I showed how to find the balance point by sliding fingers together, and we find the balance point is right to 0. Doesn't matter where I start my fingers at. You can't see them there in the camera. I have to have the center. If I slide them together, those fingers will slide to the center of mass. Okay? Then I hung weights on it. Where are they? I'll just hang some scissors on here. And let's lift this camera up a little bit. If I put a weight on it, then I can put my fingers under it, and I can slide together, and it will stay balanced, and I will end up at the center of mass. I got the scissors on there, and the bar is clearing the whole table, and it's balanced. Okay, that works because of friction. I'm not going to spend a lot of time on the friction, but the idea behind it is, if I have a bar, then there's a center of mass. If it's a uniform mass down it, there's a center of mass, which would be right in the middle. And if I hang scissors on one end of it, then the scissors will pull it down, and the center mass of the system will have to move towards the scissors. Now, one way you can analyze this is through torque. Now, torque is, if you've ever been on a teeter-totter with a little kid or as a little kid, then you put the people on each end, and the heavy person pushes it down, the little one's up. And so the heavy person has to move closer in to balance it. Or you have to put more people on with the little person to keep it balanced so it's a nice teeter-totter work. Teeter-totters work best if the two people are about the same size. Okay? Well, the mass of the bigger person causes a stronger force down, its weight, and it's working on a lever arm from the pivot point, from the fulcrum to the person. And over here we have a lighter person with a longer lever arm, and that balances a heavier person with a shorter. So the force times the length of the lever arm is called torque. Now, since I don't know where the fulcrum is, there was no fulcrum, I could say, well, let's consider there's a fulcrum right there at one end. And I could put it in the middle. I could put it under the scissors. I could put it any place. But the bar itself has a mass, and if I take it times acceleration due to gravity, I get the weight, but everything's going to be times acceleration due to gravity, so I can ignore that. I'm going to take the mass times how far the center of mass of this is. I'll call that A, mass times A. That will be it will try to turn the mass times A times acceleration due to gravity, will try to make this bar fall, which would be a clockwise rotation. And that's the mass of the bar times A. Now the scissors will also try to cause a clockwise rotation. So the mass of the scissors times the acceleration due to times its distance, which I can call B, will be a torque trying to turn it down times acceleration to gravity. What's keeping it from going down? Well, my fingers were pushing up someplace at some distance C out here, and it's pushing up with how much force? Well, enough to lift the whole bar, mass of the bar, plus the mass of the scissors. So if I set these two equal, I will get and solve for C. Let's say I know A, I know B, I know where the scissors are, I know where the center mass of the bar is, I know where the center of it is. I know these masses, I know these masses. I can solve for the center of mass. And the book will use X bar. And you can do that with the focal point here, with the focal point, the pivot point here, or the pivot, anywhere you want to put it, as long as you measure the distance from where you're putting it, times the mass, distance times the mass, distance times the masses, and you will find the center of mass. So they do that in abstract here with a bookshelf. They say, what if you have a bookshelf that's 6 feet long? 1, 2, 3, 1, 2, 3, 4, 5, 6 feet long. And here's 0, and here's 6, and you put a book here that weighs 1 pound, and you put a book here that weighs 1 pound. Where's your center of mass? Well, clearly it's at the center. That's assuming your shelf weighs nothing, or is it uniform mass, the length of it, and you do include it. Then they say, what if you put a 1 at 0, 1 at 2, 1 at 4, and 1 at 6, what's your center of mass? Well, what they're saying to do is you take, if this is 1 pound, they're asking you to do 1 times, how far is, where is it at? It's at 0. 1 times 0 plus 1 pound at 2 plus 1 pound at 4 plus 1 pound at 6 divided by the total weight, which is 1, 2, 3, 4 pounds, and you should find where the focal point is. So that's 1 times 0 is 0, plus 2, plus 4, plus 6, so that's 10, 12 divided by 4 is 3. Okay? They do it again. They put a book at 0, a book at 2, a book at 3, and a book at 6. So they're changing this to a 3, and so now they're moving this book here, and our center of mass is going to move over here. So it's going to be 2 plus 3 plus 6 is 11 divided by 4, and 11 divided by 4 will be 2 3/4. 2 3/4 will be the center of mass. And they continue doing that, and they keep trying to get you to come up with this formula. Well, I just gave it to you. And so they say you can find the center of mass by taking its position times its mass, plus the position times its mass, plus all of the positions times the mass, divided by the total mass, and you will have where the center of mass is. And if we're adding a bunch of things like this, we could also do it if there's a density on the thing that's changing. We can take the position times the density of a piece, the mass of a piece, taking the density times the piece, the volume of the piece, and then the distance. Oop, you can't see that. Let me leave that out here. So if you have a density times the volume times where it's at, plus where it's at times density times the volume of that piece, and keep doing that over the density times the volume, which gives you a mass, and a mass. So you're getting the total mass, and up here we're getting the mass times the position, and if you divide those, you'll get the center of gravity. Well, this is starting to look like what calculus does. And we get to this formula that says you can find the center of mass by taking the position times the density at that position times the volume at that position. If dx, this is assuming densities in terms of a position, and this somehow has to get to be the volume over the total mass, and we get the center of gravity. So let's see how that works. We have a bar that has this varying mass. So the total mass, which we learned at the beginning of this, is the integral from 0 to 20, because it's 20 centimeters long, of the mass, or the density, 4 plus 0.1x. So density times the volume, and it says here that this density is measured in grams per centimeter, so they've already, it must be consistent diameter, or cross section, so they've already taken out 2 of the centimeters, so all we have to do is times dx, and that will give us the mass. And let's do this. The integral of 4 is 4x. The integral of 0.1x is 0.1x squared over 2. And evaluated from 0 to 20, which is 20 times 4 is 80, plus 20 squared is 400, times 0.1 is 40, divided by 2 is 20. So we've got 100 grams, because it was grams per centimeter, and this was 0 to 20 centimeters, and that works that out. Now it says calculate the center of mass. X bar is the center of mass. So the only thing different between this and center mass is we have to do the torques, the lever arms. We have to take the integral from 0 to 20 of the position, which will be x, times the density, position times density, 4 plus 0.1x times the volume, or if this has already got part of it in there, times dx, and that will give us, see, is that right? Yes. The numerator of this, and then we divide it by the density, which the total mass, I should say, total mass, the density times the volume evaluated gives you total mass, which we already got as 100 grams. So we would have to work this out, and that will give us the center of mass. I assume you can do that and you can figure out that. Now, if they want the average density of the bar, we can find the density. If this is the density function, if you want average density, just like we did a long time ago, the average of a function is 1 over b minus a times the integral from a to b of the function. So if you want the average density, you'll calculate the total mass and then divide it by from where to where you're getting that total mass, and that was from 0 to 20. So it would be this answer divided by 20 minus 0, which is 100 divided by 20. And this is in grams, and we're dividing by AB, which is in centimeters. And we get an average density of 5 grams per centimeter. Now that's not really density because it should be times divided by centimeters cubed, but they left out that part for us, so we have to leave it out. Okay? Now consider a different density given by this, and do the same stuff. And so we'd put this in place of this thing and in place of that, and integrate that, and we can get these last two answers. Okay? So that's the introduction and what my explanation was for 6.3.